Good evening. I am Professor SHALINI SAHAY, Assistant Professor, EC Department, SIRT Bhopal. Today in this lecture, I am going to discuss about the transmission line theory. First, introduction. In an electronic system, the delivery of power requires the connection of two wires between the source and the load. At low frequency, power is considered to be delivered to the load through the wire. In the microwave frequency region, power is considered to be in electric and magnetic fields that are guided from place to place by some physical structure. Any physical structure that will guide an electromagnetic wave place to place is called a transmission line. There are mainly four types of transmission line. One is the two-wire line. Second, coaxial cables. Third, waveguide, which is of two kinds, rectangular waveguide and circular waveguides. Fourth one is planar transmission line, which consists of stripe line, microstrip line, slot line, fin line, coplanar waveguides, and coplanar slot lines. Now we analyze the difference between low and high frequencies. At low frequencies, the circuit elements are lumped since voltage and current affect the entire circuit at the same time. At microwave frequencies, such treatment of circuit elements is not possible since voltage and current waves do not affect the entire circuit at the same time. The circuit must be broken down into unit sections within which the circuit elements are considered to be lumped. This is because the dimension of the circuits are comparable to the wavelength of the waves according to the formula, where c represents the velocity of light and f represents the frequency of the voltage and current. Transmission line concepts. The transmission line is divided into small units where the circuit elements can be lumped. Assuming the resistance of the line is 0, then the transmission line can be modeled as an LC ladder network with inductors in series arms and the capacitor in the shunt arms. The value of inductance and capacitance of each part determines the velocity of propagation of energy down the line, where the time taken for a wave to travel one unit line is equals to L under root of LC or L into C the whole power of 0.5. Velocity of the wave is equals to meter per second is equals to 1 upon T, or impedance at any point it is equals to Z is equals to V at any point upon I, current at any point. Z is equals to under root of L upon C. Now line terminated in its characteristic impedance. If the end of the transmission line is terminated in a resistor equal in value to the characteristic impedance of the lines as calculated by the formula Z is equals to under root L upon C, then the voltage and currents are compatible and no reflection will occur. When line terminated in a short, when the end of the transmission line is terminated in a short resistance, that is RL is equals to 0, then the voltage at the short must be equal to the product of the current and the resistance. Line terminated in an open. When the line is terminated in an open, the resistance between the open ends of the line must be infinite. Thus, the current at the open end is 0. Now the reflection from resistive loads. When the resistive load termination is not equal to the characteristic impedance, part of the power is reflected back. then the remainder is absorbed by the load. The amount of voltage reflected back is called the voltage reflection coefficient, and it is equals to the ratio of the reflected voltage upon the incident voltage. Then the reflection coefficient is also given in terms of characteristic impedance, that is equals to load impedance minus the output impedance upon the load impedance plus the output impedance. Now we'll discuss about the standing waves. A standing wave is formed by the addition of incident and reflected waves and has nodal points that remain stationary with time. So we can say that a standing wave is the superposition of the incident wave and the reflected waves. So these points are the standing points which does not move, so it is called a standing wave. Voltage standing wave ratio is equals to V max upon V minimum. Voltage standing wave ratio expressed in decibel is called the standing wave ratio, and it is equals to 20 log 10 VSWR. The maximum impedance of the line is given by Vmax upon I minimum. The minimum impedance of the line is given by V minimum upon the I maximum, or Z minimum is equals to Z naught upon VSWR. Relation between voltage standing wave ratio and the reflection coefficient is given by the formula 1 plus mod of G upon 1 minus mod of G, or G is equals to VSWR minus 1 upon VSWR plus 1. Now the general input impedance equation. Input impedance of a transmission line at a distance L from the load impedance ZL with a characteristic impedance Z0 is equals to Z input is equals to Z0 into ZL plus J Z0 BL whole upon Z0 plus J ZL BL, where B is called the phase constant or wavelength constant, and it is defined by the equation 2 pi upon lambda. Thank you.